Let me give you a number. 4 million. That is the number of times more massive than our Sun that the object at the center of our galaxy is. 4 million solar masses, compressed into a region of space roughly the size of our inner solar system. Sitting 27,000 light-years away, in the direction of the constellation Sagittarius, at the heart of the Milky Way, there is something that has no clean name. Not really. We call it Sagittarius A star. We have taken its photograph. We have watched stars orbit it for decades at speeds that defy comprehension. We have measured the size of its shadow against the backdrop of radio wave emissions. And what we have found has cracked something fundamental, not in the object itself, in us, in our models, in the two most successful theories in the history of science, which, when applied simultaneously to this object, produce answers that cannot both be true. Here is what tonight is really about. It is not about a black hole. Black holes are old news at this point. The Event Horizon Telescope gave us photographs. The Laser Interferometer Gravitational Wave Observatory confirmed mergers. We have the receipts. Tonight is about what black holes do to time, and not in the way science communicators usually explain it, not the soft version. Not the clocks run slower near heavy objects version that you absorbed from a documentary and filed away as interesting. We are going inside the machinery tonight. We are going to sit inside the mathematics and look at what the equations actually say. And then we are going to sit with the fact that two sets of those equations, both confirmed by experiment, both verified to extraordinary precision, say completely incompatible things about what happens to time at the most extreme gravitational boundary in the known universe. That incompatibility is not a philosophical curiosity. It is the largest unresolved problem in physics. And what makes it a compound hazard in the Crisis Horizon Labs framework is not merely that the physics is broken, it is that this rupture in our theoretical infrastructure has direct downstream consequences for every model we use to describe the fate of matter, the conservation of information, the arrow of causality, and the limits of human knowledge about the nature of reality. Two systems, overlapping, neither one capable of fully describing what the other requires. And the place where they collide is right there at the edge of a black hole, right there at the event horizon, at the precise boundary where time, as you understand it, ceases to function normally. That is where we are going tonight. Before we begin, I want to ask you something simple. Drop your current location and local time in the comments. City, country, hour of the day. I ask this every time. It is not a quirk. It is a reminder that you are somewhere specific in space and time right now, and that where you are sitting is actually relevant to what we are about to discuss. Because time dilation is not something that only happens near black holes. It is happening to you, right now, in a measurable way, because of where you are in Earth's gravitational field. By the time this video ends, you will understand what that means, and it will not feel trivial anymore. Let us begin. Part 1. The machinery. What time actually is, according to the physics. Most people treat time as background. As a canvas, time is the thing that passes while events happen inside it. Newton thought the same. He called it absolute time, a river flowing at the same rate everywhere in the universe, indifferent to mass, velocity, or the presence of anything else. A universal clock ticking in perfect synchrony from the Big Bang to the last photon. That picture is wrong. It is not approximately wrong in edge cases. It is structurally wrong at a deep level, and the person who showed us why is Albert Einstein, in two papers published over a decade apart. The first, the special theory of relativity, arrived in 1905. The second, the general theory of relativity, arrived in 1915. Together they constitute what we now call relativistic mechanics, and they represent the most rigorously tested theoretical framework in the history of science. Here is what they tell us about time. Time is not background. Time is a dimension, woven together with the three spatial dimensions into a single four-dimensional fabric called space-time. That fabric is not rigid. It bends, it stretches, it warps in the presence of mass and energy. And the rate at which time flows at any given point in that fabric depends on two things: how fast that point is moving relative to another point, and how deep it sits in a gravitational well. This is not a metaphor. This is geometry. This is the actual structure of the universe as described by Einstein's field equations, which are a set of 10 coupled, nonlinear, partial differential equations that relate the curvature of spacetime to the distribution of mass and energy within it. Those equations have been tested to extraordinary precision. The predictions they make are not close. They are exact, within measurement uncertainty, every single time we check. Let me give you 3 examples that are not theoretical. The global positioning system. You use it every day. The satellites that make it work orbit Earth at roughly 20,000 kilometers of altitude. Up there, gravity is weaker than it is on the ground. Einstein's equations predict that clocks in weaker gravity run faster than clocks in stronger gravity. The satellites also move at orbital velocity, which, according to special relativity, causes their clocks to run slightly slower. When you combine both effects, the net result is that satellite clocks gain approximately 38 microseconds per day relative to clocks on the ground. 38 millionths of a second. That sounds trivial. But because global positioning system works by measuring tiny time differences between signals from multiple satellites, a 38 microsecond error compounds rapidly. If engineers did not correct for relativistic time dilation, global positioning system coordinates would drift by roughly 10 kilometers per day. Your phone would place you in a different city. Every navigation system on Earth compensates for Einstein's equations, every single day, because those equations are correct. Second example. In April 2024, the Office of Science and Technology Policy at the White House issued a formal memorandum acknowledging that time on the lunar surface runs at a measurably different rate than time on Earth. The Moon sits in a shallower gravitational potential than Earth, which means lunar clocks tick faster relative to Earth-based clocks by an average of 58.7 microseconds per Earth day, with additional periodic variations. The memo acknowledged that synchronizing technological infrastructure between the Moon and Earth requires explicit relativistic correction. The American government has formally recognized that time on the Moon is not the same as time on Earth. This is not science fiction. It is policy. Third example. In 1971, physicists Joseph Hafele and Richard Keating put atomic clocks on commercial aircraft and flew them around the world. When the flying clocks were compared to stationary clocks on the ground, the results matched relativistic predictions precisely. Time had measurably passed at different rates on the plane than on the surface. This experiment has been replicated many times with increasing precision. Every result confirms Einstein, so time dilation is not exotic. It is not a theoretical curiosity. It is a real, measurable, currently compensated for phenomenon that affects the technology you use this morning to find a coffee shop. The question we are building toward is, what happens when you dial the gravitational field up from surface of Earth to event horizon of a black hole? The answer will take the rest of this video. Keep that thought. We are going to need it. Part 2. The Schwarzschild threshold, non-rotating black holes, and the mathematics of frozen time. In 1916, 1 year after Einstein published the general theory of relativity, a German physicist and astronomer named Karl Schwarzschild found the first exact solution to Einstein's field equations. Schwarzschild was serving on the Russian front during the First World War when he derived the solution. He sent it to Einstein from the trenches. He died a few months later from an illness contracted at the front. The solution he found describes the geometry of space-time around a perfectly spherical, non-rotating, uncharged mass. A point mass with nothing else in the universe. Clean, idealized, exact. The result is what we now call the Schwarzschild metric, and it contains something remarkable. At a specific distance from the center of any mass, there is a radius at which the mathematics of space-time geometry breaks down. Or rather, not breaks down, changes in kind. The radius is called the Schwarzschild radius, and the formula for it is deceptively simple. It equals 2 times the gravitational constant times the mass of the object, divided by the speed of light squared. For a mass equal to our Sun, the Schwarzschild radius is approximately 3 kilometers. Compress all of the Sun's mass into a sphere 3 kilometers in radius, and something catastrophic happens to the space-time around it. For Earth, the Schwarzschild radius is about 9 millimeters, the size of a marble. For a human being, it is on the order of 10 to the minus 23rd meters, which is smaller than an atomic nucleus. These are not real black holes. They are thought experiments. But the mathematics does not care. If any mass is compressed below its Schwarzschild radius, the Schwarzschild metric describes what happens to space-time around it. And what happens is this. The gravitational time dilation factor, derived from the Schwarzschild metric, takes a specific mathematical form. The rate at which time passes at a given radius from the black hole, relative to a distant observer far from the black hole, depends on how close that radius is to the Schwarzschild radius. As the radius approaches the Schwarzschild radius from the outside, the time dilation factor approaches zero. Time slows down. Not metaphorically, not approximately. The factor in the equation goes to zero. At the Schwarzschild radius, a mathematical singularity appears. Not the singularity at the center of the black hole, a different one. A coordinate singularity at the surface called the event horizon. The passage of time for an object approaching a black hole slows dramatically relative to a distant observer as it nears the event horizon. This phenomenon results from gravitational time dilation, compounded in many cases by relativistic effects due to high orbital velocities. Here is what that means in practice, and I want you to sit with this carefully. Imagine an astronaut falling feet first toward the event horizon of a Schwarzschild black hole. She is wearing a watch. She is also being observed from a great distance by a second astronaut in a stationary ship far from the black hole. From the falling astronaut's perspective, time passes normally. Her watch ticks once per second. The crossing of the event horizon happens in finite time. She feels nothing special as she crosses. She continues into the interior. Her subjective experience of time is uninterrupted. For the astronaut, proper time flows normally. Their wristwatch ticks at a steady rate. As they cross the event horizon, they do not feel any sudden change in time. The crossing happens in finite proper time. Now look at the same event from the distant ship. The distant observer watches the falling astronaut through a telescope. As the astronaut falls closer to the event horizon, something strange begins to happen. The light signals from the astronaut take longer and longer to arrive. Her image appears to slow down. Her movements become sluggish. Light signals from the astronaut become increasingly redshifted and arrive more infrequently, taking longer and longer to reach the distant observer. The distant observer never actually sees the astronaut cross the event horizon. From the distant ship, the astronaut appears to slow to a halt. Her image freezes at the edge of the event horizon, growing redder and dimmer as photons climbing out of the intense gravitational field lose energy. She appears to hover at the boundary forever. She never appears to cross, but she crossed, in finite proper time, instantly. From her perspective, two observers, one event, two radically different descriptions of when that event occurred, and whether it occurred at all within any finite time frame. Neither observer is wrong, neither is experiencing an illusion. Time itself is behaving differently for each of them, and both descriptions are geometrically valid within Einstein's framework. This is not a paradox that physics has resolved into something comfortable. When physicists research black holes, particularly the event horizons, the paradox emerges of how gravitational time dilation freezes time for a distant observer. There are coordinate systems that mathematically smooth over this apparent conflict, but those coordinate systems carry their own complications, and the underlying physical question of what time really is near an event horizon remains philosophically contested among physicists at the frontier of the field. What is not contested is the mathematics. The Schwarzschild metric produces gravitational time dilation that diverges to infinity at the event horizon, not to a large number, to infinity. Time, as measured by a distant observer, slows completely to a stop at the event horizon's surface. An object falling in appears to take infinite external time to cross a boundary that it crosses in finite internal time. The Schwarzschild radius for the black hole Sagittarius A star, at the center of our galaxy, is approximately 12 million kilometers. For comparison, the Sun's diameter is 1.4 million kilometers. The event horizon of the black hole at the center of our galaxy is nearly 8 times wider than the Sunday. A human could not feel tidal forces near the event horizon of a black hole this massive. You would cross it without physical sensation, but you would cross it in a region of spacetime where time, to the outside universe, appears to have stopped. There is something here that demands we pause and ask a harder question. If time dilation is infinite at the event horizon, does the event horizon actually exist? Can it ever fully form from the perspective of the outside universe? If nothing ever appears to cross it, does the interior of a black hole exist in any operationally meaningful sense to an external observer? The answer, according to general relativity, is yes. The interior is real. The crossing happens. But the proof of that reality can never, by definition, be transmitted to anyone outside the event horizon. The information is causally disconnected from the universe we live in, and that is only the first layer of the problem. Part 3. The Kerr monster. Carl Schwarzschild's solution was elegant, but it described an idealized object, a perfectly still, perfectly spherical mass with no rotation whatsoever. Real black holes are not like that. Real black holes form from the collapse of massive stars, which rotate. They form from the merger of neutron stars or other black holes, which orbit each other. Conservation of angular momentum means that when a rotating progenitor collapses into a black hole, the resulting object spins, not slowly, extremely fast. Some black holes are thought to rotate at close to the theoretical maximum, which corresponds to a state in which the event horizon radius is exactly half of the Schwarzschild radius for the same mass. It was not until 1963, nearly 5 decades after Schwarzschild, that New Zealand mathematician Roy Kerr found the exact solution to Einstein's field equations for a rotating black hole. The Kerr metric is considerably more complex than the Schwarzschild metric, and what it describes is considerably more violent. A rotating black hole does not merely curve spacetime around it. It drags spacetime, physically. The rotation of the black hole pulls the fabric of spacetime itself into rotation around it, like the surface of a whirlpool pulling water. Except the whirlpool here is 4-dimensional, and what is being dragged is not water, but the coordinate structure of reality itself. This phenomenon is called frame dragging, or the Lentz-Thurring effect. Unlike the non-rotating Schwarzschild black hole, the Kerr black hole possesses spin, which significantly affects the spacetime around it. This rotation introduces frame dragging, a phenomenon where spacetime itself is twisted in the direction of the black hole's rotation. Objects and light near the black hole are influenced by this effect, causing them to co-rotate with the black hole. Frame dragging exists around any rotating massive object. Earth produces it. We have measured Earth's frame dragging effect using the Gravity Probe B satellite. It is tiny, measurable, but tiny. Near a rapidly rotating stellar mass black hole, it is not tiny. It is catastrophic. This is particularly noticeable in the region known as the ergosphere, which lies just outside the event horizon. Within the ergosphere, no object can remain stationary. It is forced to rotate along with the black hole due to the dragging of spacetime. The ergosphere is a region outside the event horizon. You are not yet inside the black hole. You have not yet crossed the point of no return. But in the ergosphere, you cannot stand still. No matter how powerful your rocket engines, no matter how much thrust you apply in the anti-rotational direction, you cannot remain stationary relative to the distant stars. Spacetime itself is moving, and you are moving with it, faster than the speed of light relative to the external frame. Because of this dragging effect, an object within the ergosphere cannot appear stationary with respect to an outside observer unless that object would be moving faster than the speed of light. The speed necessary for such an object to appear stationary decreases at points further out from the event horizon, until at some distance the required speed is negligible. Now add this to the time dilation picture and watch what happens. In the Schwarzschild geometry, time dilation depends only on your radial distance from the center. Get closer to the event horizon, time slows. Simple. In the Kerr geometry, time dilation depends on your radial distance and on whether you are co-rotating or counter-rotating with the black hole, and on your polar angle relative to the rotation axis, and on the spin parameter of the black hole itself. The implications are not academic. A particle orbiting a maximally spinning Kerr black hole in the prograde direction, meaning orbiting in the same direction as the black hole's rotation, can get considerably closer to the event horizon than a particle orbiting in the retrograde direction before reaching its innermost stable orbit. This is because frame dragging acts like a boost for prograde motion. It effectively carries the orbital energy of the particle along with the rotation of spacetime. The innermost stable circular orbit of a maximally spinning Kerr black hole, in the prograde direction, coincides with the event horizon itself. This is the regime explored in the film Interstellar, which physicist Kip Thorne, a Nobel Prize winner in physics, served as scientific advisor for. The fictional planet Miller, orbiting in the extreme proximity of the fictional black hole Gargantua, experiences a time dilation ratio of approximately 1 hour on the planet to 7 years outside the black hole's influence. Intuitively, Even an expert in general relativity would estimate it impossible to reconcile an enormous time differential with a planet skimming up near the event horizon and safely enduring the correspondingly enormous gravitational forces. However, Thorne did a few hours of calculations and came to the conclusion that, in fact, it was marginally possible, although very unlikely. The key point is the black hole's spin. A rotating black hole, described by the Kerr metric, behaves rather differently from a static one described by the Schwarzschild metric. The mathematics of the Kerr metric for time dilation produces a ratio that, for an orbit barely inside the ergosphere of a near maximally rotating black hole, allows for extreme time differentials without tidal destruction. The film's science, at least on this point, is not wrong. It is unlikely, but it is not wrong. And the Kerr geometry produces something else, something with no equivalent in the Schwarzschild picture, something called the Penrose process. Roger Penrose, the British mathematical physicist who shared the 2020 Nobel Prize in Physics for his theoretical work on black holes, proposed in 1969 that the ergosphere of a rotating black hole can be used to extract energy from the black hole itself. A projectile disintegrates into the ergosphere. One of the fragments falls into the event horizon in a direction opposite to the black hole's rotation, while the other fragment can leave and be recovered, carrying more energy than the initial projectile. Let that sit for a moment. You can extract energy from a black hole. You can throw something in and get more back, not by violating thermodynamics. By harvesting the rotational kinetic energy of the spinning black hole, which decreases slightly with each extraction, the black hole slows down, infinitesimally, every time you do it. The ergosphere is a region where the black hole's rotational energy is effectively accessible to the outside universe. Frame-dragging effects near rotating black holes enable the Penrose process, which is the extraction of rotational energy, by dropping material into the ergosphere, a mechanism potentially powering relativistic jets in active galactic nuclei and gamma-ray bursts. This is not theoretical speculation. The jets we observe launching from active galactic nuclei, columns of plasma accelerated to 98% of the speed of light and extending for millions of light-years, are almost certainly powered by the Penrose mechanism or a closely related magnetic variant called the Blandford-Znaic process. The most energetic, sustained phenomenon in the universe is a direct consequence of what rotation does to the geometry of time near a black hole. Spinning black holes introduce even more dramatic spacetime distortion. Black hole science shows that rotation drags spacetime itself, a phenomenon known as frame dragging. This effect was experimentally confirmed and is especially intense near rapidly rotating Kerr black holes. I want you to notice something. We have now described two very different kinds of black holes, Schwarzschild and Kerr, and in both cases the behavior of time at or near the event horizon is not just unusual, it is structurally incompatible with everyday experience. In both cases, the mathematics produces well-defined, exact answers. In both cases, those answers have been tested against observation, against the behavior of accreting gas, against the shapes of relativistic jets, against the orbital mechanics of stars near Sagittarius A star, and they match. But both of these solutions, the Schwarzschild solution and the Kerr solution, are solutions to the equations of general relativity, and general relativity is half of the problem. The other half is quantum mechanics. And when you bring them together at the event horizon, the floor gives way. Is this a coincidence, or is there something deeper here? Something that our frameworks were never designed to encounter? Drop your thoughts in the comments. Part 4. The Quantum Rupture. What happens when the two greatest theories in physics cannot both be true? General relativity and quantum mechanics are the two pillars of modern physics. Together, they describe virtually everything we observe. General relativity governs the large scale. Gravity, the curvature of spacetime, the dynamics of galaxies, the behavior of black holes. Quantum mechanics governs the small scale, the behavior of particles, the interactions of forces at subatomic distances, the probabilistic structure of matter at its most fundamental level. Both theories are extraordinarily successful. Both are confirmed by experiment to precision levels that would have seemed impossible a century ago. And both, at the event horizon of a black hole, make predictions that cannot simultaneously be true. This is not a minor tension. This is not a rounding error or a loose end. This is a hard incompatibility at the precise location where time dilation is most extreme. The place where our theoretical understanding of time is being stretched to its absolute limit is also the place where the two best theories we have break each other. Let us start with Stephen Hawking. In the 1970s, Hawking applied quantum field theory to the space-time geometry near a black hole event horizon. Quantum field theory, the framework that describes fundamental particles as excitations in quantum fields, predicts that empty space is not actually empty. The vacuum seethes with virtual particle-antiparticle pairs, constantly popping into existence and annihilating each other, borrowing energy from the quantum vacuum for vanishingly short intervals. This process, called vacuum fluctuation, is experimentally confirmed. The Casimir effect, a measurable attractive force between two closely spaced metal plates in vacuum, is direct evidence of it. Near the event horizon of a black hole, Hawking realized something remarkable happens to these vacuum fluctuations. Normally, the particle and antiparticle in each pair annihilate before anything real occurs. But at the event horizon, if a pair appears with one particle on the outside and one on the inside particle is trapped. It cannot escape. The outside particle, however, suddenly has no partner to annihilate with. It becomes real, many dagro. It flies away from the black hole carrying energy. And where does that energy come from? From the black hole's mass itself. The black hole loses mass, slowly, over an immense timescale for large black holes. But inevitably, the black hole evaporates. This is Hawking radiation. When the laws of quantum mechanics are applied to the sphere around a black hole where light can no longer escape, called its event horizon, radiation should be emitted by the black hole. This means the black hole slowly evaporates. For a stellar mass black hole, the evaporation timescale is orders of magnitude longer than the current age of the universe. But the principle is not in question among physicists. Hawking radiation is the theoretical consensus. The problem is not whether it happens. The problem is what it carries. Quantum mechanics has a principle called unitarity. Unitarity says that information is never destroyed. If you know the complete quantum state of a system at any point in time, you can, in principle, reconstruct the state at any earlier point in time and predict the state at any later point in time. The universe at the quantum level is deterministic in both directions. Information is conserved. Hawking radiation, which contains only some of the information of whatever is sucked in by a black hole's all-consuming gravity, will eventually cause the black hole to totally evaporate, which creates a paradox. If the Hawking radiation that slowly evaporates a black hole carries no information about what fell in, then when the black hole is gone, that information is gone. A star, a planet, a billion years of complexity, reduced to featureless thermal radiation, and then to nothing. Gone. Unitarity violated. A foundational principle of quantum mechanics destroyed. This is the black hole information paradox, and it is not a niche problem. The black hole information paradox presents a sharp conflict between quantum theory and general relativity, and so is an important clue to their unification. It was raised by Hawking in the 1970s and has occupied some of the most brilliant minds in theoretical physics for the 5 decades since. It remains unsolved. But in 2012, a group of physicists at the University of California at Santa Barbara, Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, proposed something that made the problem dramatically worse. Their paper, widely known by the initials of the 4 authors as the Almheiri-Marolf-Polchinski-Sully paper, argued that you cannot simultaneously maintain 3 things that everyone had assumed were true about black holes. The 3 things are: first, the information in Hawking radiation is preserved. Unitarity holds. Second, general relativity's equivalence principle is valid at the event horizon. An infalling observer feels nothing special as they cross. The event horizon is locally smooth. Third, an observer far from the black hole sees physics that is consistent with standard quantum field theory. Almheiri-Marolf-Polchinski-Sully pointed out that local quantum field theory, unitarity, and no drama, the assumption that infalling observers should not experience anything unusual at the event horizon if the black hole is sufficiently large, cannot all be consistent with each other. Something has to give. You can have 2 of those 3 things. You cannot have all 3. The Almheiri-Marolf-Polchinski-Sully paper then argued for what they called the most conservative resolution. If unitarity must hold, and if the information in Hawking radiation is genuinely encoded in correlations at the event horizon, then the event horizon cannot be smooth. Instead of the quiet, locally empty space that general relativity predicts an infalling observer would experience, the event horizon should be replaced by a wall of highly energetic quanta, a curtain of fire, a firewall. Essentially, the paradox says that for a black hole, the assumption that a free-falling observer senses nothing special when crossing the event horizon contradicts a unitary quantum theory. Actually, this assumption is just the equivalence principle, which is the foundation of general relativity. General relativity and unitary quantum theory sharply conflict with each other. If the firewall interpretation is correct, then what we said in Part 2 about the astronaut crossing the event horizon in finite proper time without sensation is wrong. She does not have a quiet crossing. She is incinerated at the boundary. General relativity's equivalence principle fails at the event horizon. If the equivalence principle is maintained, and the crossing is smooth, then either Hawking radiation does not carry information in the way quantum mechanics requires, or quantum field theory breaks down at cosmological distances from the black hole. Neither is acceptable without revolutionary new physics. The firewall proposal challenges this expectation by arguing that such smoothness cannot be maintained if unitarity is required. There are other proposed resolutions. The complementarity principle, developed by Leonard Susskind and others, argues that no single observer ever sees both the falling-in information and the Hawking radiation simultaneously, so no actual paradox is observed. The island formula, developed more recently, proposes that when Hawking radiation is accounted for, the quantum state of the radiation after sufficiently long evolution includes quantum corrections that encode the interior information. Some physicists have proposed that the interior of the black hole is not a separate region, but is somehow the same region as the exterior, connected by quantum entanglement in a way described by the conjecture that relativity in the interior equals entanglement in the exterior. This conjecture goes by the shorthand of Einstein-Rosen equals Einstein-Podolsky-Rosen, or the idea that wormholes and quantum entanglement are fundamentally the same thing. None of these proposals is accepted consensus. All of them require physics beyond what we currently have confirmed. And the common thread through all of them is this. The breakdown occurs right where time dilation is infinite. At the event horizon, at the boundary where time, as seen from outside, stops completely. The intersection of infinite time dilation from general relativity and the quantum informational demands of Hawking radiation is where our entire theoretical framework for describing physical reality currently fails. Let that land. Our two best theories, both confirmed, both essential, both in active use, right now, in technologies that work, pointing at the same boundary in space and producing contradictory answers about what is there. That boundary is defined precisely by time dilation. It is the surface where the time dilation factor goes to infinity that is the locus of the crisis. This is the compound hazard. This is the nonlinear interaction, not just extreme physics, not just hard mathematics. Two independently validated, functionally correct theoretical systems colliding at the exact point where time becomes singular, and we do not have a resolution. Part 5. The geometry of the abyss. What happens inside, and why the question may be unanswerable. Let us go deeper. Let us cross the event horizon and ask what the physics of time looks like on the other side. In the Schwarzschild geometry, crossing the event horizon does something peculiar to the coordinates. In the exterior of the black hole, the radial coordinate, the distance from the center, is a spatial dimension. You can move toward the center or away from it. It is a direction you can choose. The time coordinate, by contrast, is what it always is. The direction of causality. Events happen in temporal sequence, one after another, and you cannot go backward. Inside the event horizon, these roles swap. In the interior of a Schwarzschild black hole, the radial coordinate becomes time-like. It is no longer a direction in space. It is a direction in time. Moving toward the singularity at the center is not moving in a spatial direction. It is moving toward the future. The singularity is not a place. It is a moment that lies in the future of every interior observer, unavoidably, with the same inevitability that tomorrow lies in your future. You cannot avoid the singularity for the same reason you cannot avoid next Tuesday. This is deeply strange and rarely explained correctly. The common picture of a black hole as a region of space you fall into, with a dangerous object at the center that you must avoid, is wrong. You do not fall toward the singularity. You fall toward the future. The singularity is a temporal boundary, not a spatial one. Once you cross the event horizon, every direction points inward. Space itself curves so severely that all paths lead to the singularity at the center. You cannot turn around. You cannot fire rockets to escape. The concept of escape loses meaning. You have entered a region of space-time disconnected from the outside universe. The singularity at the center of a Schwarzschild black hole, described by the mathematics of general relativity, is a point where the curvature of space-time becomes infinite. Density is infinite. Pressure is infinite. Time itself, as a concept, reaches a terminus. The equations produce divergences that signal the complete breakdown of general relativity as a theory. The mathematics is telling us that general relativity is not valid at that point. It requires extension by a more complete theory which we do not yet have. In the Kerr geometry, the situation is even more complex. The singularity of a rotating black hole is not a point, it is a ring of infinite curvature lying in the equatorial plane. And the Kerr metric, extended to its maximal analytical form, produces something that is almost certainly unphysical but is mathematically present. A second event horizon inside the first, and the geometric possibility of a region beyond the inner horizon where the singularity is avoidable, and where the time and space coordinates flip back to their normal roles. The Kerr metric even produces, mathematically, the possibility of closed time-like curves in the interior, paths through space-time that loop back on themselves and arrive at their own starting point, time travel, in the crudest sense of the term. But physicists universally believe this is an artifact of the idealized mathematics, not a feature of real rotating black holes. Roger Penrose's cosmic censorship conjecture, and subsequent work by Penrose and Stephen Hawking, suggests that the inner horizon of a real Kerr black hole would be unstable. It would be replaced by a different kind of singularity generated by the blue shifting of infalling radiation, which grows without bound as it accumulates near the inner horizon. The interior of a real astrophysical black hole is, in short, a region we can describe mathematically but that lies permanently outside the reach of empirical verification. Nothing that enters it can ever report back. No experiment can probe it. The laws of physics, as we know them, break down at its core. And yet these objects exist. They are not theoretical curiosities. Sagittarius A star is 27,000 light-years away, but it is real. The observations revealed a bright ring of emission from the superheated accretion disk surrounding Sagittarius A star, and confirmed that it is indeed a supermassive black hole with an event horizon, a surface beyond which nothing, including light, can escape the black hole's immense gravitational pull. The Event Horizon Telescope image is not an artist's rendering. It is a direct measurement, assembled from radio observatories on multiple continents working together to achieve a resolution equivalent to reading a newspaper in New York from a sidewalk in Paris. Sagittarius A star. 4 million solar masses. Event horizon 12 million kilometers wide, sitting at the center of the galaxy we inhabit, and at its surface time dilation is not 38 microseconds per day. Not 58 millionths of a second per day. It is infinite. Infinite time passes for the outside universe for every finite moment of proper time at the horizon. The Event Horizon Telescope collaboration has released multiple sets of observations and is now developing the next generation of the array. The first images of the black holes in Sagittarius A star and Messier 87 have created a wide range of new scientific opportunities in gravitational physics, compact objects, and relativistic astrophysics. The next generation Event Horizon Telescope will be able to image the photon ring, the bright feature formed by light that has orbited the black hole multiple times before escaping. The enhanced sensitivity and resolution of the Event Horizon Telescope will allow scientists to study the complex dynamics of accreting material in magnetically arrested accretion disks, which are present in many supermassive black holes, including those at the centers of Messier 87 and Sagittarius A star. The photon ring is a direct measurement of time dilation in action. Light circling the black hole multiple times before escaping has spent more time in the extreme gravitational field. Its wavelength is stretched. Its frequency is shifted. The rings encode, directly in their spacing and brightness ratios, the gravitational geometry that produces the time dilation we have been discussing. We are not speculating. We are measuring. What we are measuring is the largest gravitational time dilation gradient that exists in the observable universe in our cosmic vicinity. And what we are finding is that our models, up to the event horizon, are extraordinarily accurate, and beyond the event horizon are guaranteed to be incomplete. One more piece of the measurement story deserves specific attention because it connects the abstract mathematics of the Kerr metric to real objects that real people have actually watched: the stars of the galactic center. Since the early 1990s, two independent groups of astronomers have been tracking the orbits of stars in the central arcsecond of our galaxy, a region of sky so small that you would need a circle roughly 3 million times narrower than the full moon to contain it. One group, led by Andrea Ghez at the University of California at Los Angeles, used the Keck telescope in Hawaii. The other, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, used the Very Large Telescope in Chile. Both groups received the Nobel Prize in Physics in 2020 for their work, shared with Roger Penrose. What they found is this: dozens of stars orbit the central point of the Milky Way with periods ranging from a few years to a few decades. The most spectacular is designated star Stu. Its orbital period is approximately 16 years. At the closest point of its elliptical orbit, its periapsis, star Stu passes within roughly 120 astronomical units of Sagittarius A star. 1 astronomical unit is the average distance between Earth and the Sunday. 120 of those. Star Stu, at periapsis, is moving at approximately 3% of the speed of light. At that velocity and that proximity, the combined effects of special relativistic time dilation from its orbital speed and general relativistic gravitational time dilation from the black hole are both measurable in the light we receive from the star. Both groups have now detected the relativistic redshift of star Stu's light as it passes periapsis. The measurements agree with the predictions of general relativity, not approximately, to within the measurement uncertainties of the observation. Star Stu is a clock orbiting the most extreme gravitational environment in our galaxy. And every 16 years, when it passes closest to Sagittarius A star, we can read that clock from Earth and verify that general relativity is correctly predicting how time dilates in the strong field regime of a supermassive black hole. Those are the receipts. The theory is tested. The time dilation is real. Part 6. The coverage gap. Why this crisis is not getting the attention it deserves, and what that means. Here is what we need to talk about, and what rarely gets a full hearing. The incompatibility between general relativity and quantum mechanics at the event horizon is not just a problem for theoretical physicists. It is a fundamental gap in the foundation of our scientific infrastructure, and it is not being treated as the emergency it arguably is. In every other domain of physics where we operate, we have a working framework. We know the applicable theory. We apply it. It predicts the outcome. We verify the prediction. Chemistry, nuclear physics, condensed matter, optics, cosmology at large scales, the physics of stars and planets and galaxies. We have frameworks that work. We may not understand everything, but we have models that produce accurate predictions within their domains of applicability. At the event horizon, we do not have a working framework. We have two frameworks that are both partially valid and mutually exclusive in their predictions, and the quantity that defines the boundary between them is time dilation. This matters for reasons that extend beyond abstract theory. Our models of the early universe rely on understanding physics at extreme energy densities. The universe began in a state of extreme density, and the physics of that state, particularly the period called the Planck epoch, the first 10 to the minus 43 seconds after the Big Bang, requires a theory of quantum gravity, a theory that describes quantum mechanics and space-time curvature together in a consistent framework. We do not have that theory. The event horizon problem, the firewall paradox, the information loss problem, these are all symptoms of the same underlying absence. Our models of what happens to matter in the final stages of black hole evaporation are undetermined. The endpoint of Hawking evaporation, when a black hole has radiated away enough mass that its radius approaches the Planck length, roughly 10 to the minus 35 meters, is a regime where quantum gravity must become important. We have no consistent prediction for what happens there. Does the black hole evaporate completely, releasing all its information in the final burst? Does it leave a remnant? Does it form something else? We do not know. Our understanding of the information content of spacetime itself is unresolved. The holographic principle, proposed by Gerard Hooft and developed by Leonard Susskind, suggests that all the information contained in a volume of space is encoded on its boundary surface, just as a hologram encodes a three-dimensional image on a two-dimensional film. This proposal emerged directly from attempts to resolve the information paradox. If it is correct, it has radical implications for what space-time, matter, and information fundamentally are. It implies that the three-dimensional world we inhabit might be, in a precise mathematical sense, a projection of a two-dimensional quantum system. The time dilation geometry at the event horizon is directly related to this holographic encoding. But the holographic principle, while enormously influential and mathematically productive, has not been confirmed as a physical law. It is a conjecture, albeit a very well-supported one. And here is the coverage gap that bothers me most. Not the scientific gap, though that is extraordinary, the human gap. Time dilation near black holes is typically communicated to the public as a curiosity, a puzzle, something interesting to think about, an occasion for metaphors about clocks and twins and space travel. The discussion almost always stays at the pop science level of time slows down near gravity. Isn't that wild? What rarely gets communicated is the severity of the crisis at the next level of depth. The fact that the place where time dilation is most extreme is also the place where our entire theoretical framework for describing physical reality collapses. The fact that this is not a solved problem with a known solution waiting to be discovered, but an active, unresolved fundamental conflict that has occupied the best mathematical minds in physics for 5 decades with no consensus resolution in sight. The coverage gap is not geographic in the way that Crisis Horizon Labs usually uses that phrase. A hurricane threatening a remote coastline does not get the same news energy as a hurricane threatening Miami. We understand that pattern, but there is an analogous effect in physics communication, where problems located at the frontier of theory, removed from immediate practical consequence, do not get the attention proportional to their depth. The black hole information paradox does not make the news. The firewall crisis does not trend. The failure of our two best theories to agree about what happens to time at the event horizon of a structure that unambiguously exists in our galaxy, 27,000 light-years away, is discussed in academic papers and conference rooms, and almost never reaches the broader conversation about the state of human knowledge. That gap is not acceptable, not because the physics is urgent in a disaster preparedness sense, though there are indirect links to cosmological models that do matter, but because the honest state of human knowledge is that the most successful scientific program in history has produced two verified frameworks that are broken against each other at the most extreme conditions that actually occur in the universe. That is remarkable. That deserves more than a footnote. We are not finished with physics. We are not at the end of the story. At the event horizon, the story is interrupted, and we do not know the next chapter. Part 7. The instruments we are building. What the next decade of observations will reveal, and what they cannot. Let me tell you what we are actually going to learn, and what the limits of that learning are, because the distinction is important. The next generation Event Horizon Telescope will significantly improve the angular resolution and sensitivity of our observations of Sagittarius A star and Messier 87 star. It will allow, for the first time, the construction of dynamic images, not just photographs but films. Moving images of the accretion disk, the swirling superheated plasma falling into the black hole, captured over timescales of hours. Through enhancements over this period, the Event Horizon Telescope will create the first movie of Messier 87, star-connecting black hole and jet physics, provide detailed studies of the structure and dynamics of Sagittarius A star, characterize the magnetospheres of both systems through polarimetric imaging, and explore the space-time properties of black holes with greater precision and range. The polarimetric imaging is particularly significant. When the Event Horizon Telescope measured the polarization of light from the accretion disk of Sagittarius A star, it was measuring the orientation of the electromagnetic field of photons emitted by material orbiting the black hole. The polarization pattern encodes information about the magnetic field geometry in the accretion disk. That geometry, in turn, is directly linked to how the black hole's gravitational field, including the frame dragging of the Kerr metric, is organizing the infalling plasma. The Event Horizon Telescope did more than just measure the brightness of the glowing gas surrounding Sagittarius A star. It also measured the light's polarization. These are measurements of time dilation in action. The precise size and shape of the photon ring, the spacing of the nested rings produced by light that has orbited the black hole different numbers of times, the degree of asymmetry introduced by the black hole's rotation. All of these observable features are direct consequences of the gravitational and frame-dragging time dilation physics we have been describing. Each measurement is another confirmation of the Kerr metric in the strong field regime, and that confirmation is important. But here is the limit. All of these observations occur outside the event horizon. Every photon that reaches our telescopes originates in the external universe. The interior of Sagittarius A star, the region where the time dilation factor exceeds any finite value, where the singularity awaits, where the quantum gravity crisis is located, is and will remain empirically inaccessible by any means consistent with the physics we understand. No observation from Earth, no matter how sensitive the instrument, can ever provide direct evidence of what happens beyond the event horizon. This is not a practical limitation. It is a fundamental one. It is baked into the causal structure of space-time as described by general relativity. The event horizon is a one-way membrane in the causal structure of space-time. Information flows inward across it, but never outward. Any physics that occurs inside is causally decoupled from our observable universe. The Laser Interferometer Gravitational Wave Observatory and its planned successors, including the space-based Laser Interferometer Space Antenna, can detect the gravitational waves produced by black hole mergers. These waves carry information about the external geometry of the merging black holes, their masses, their spins, the orbital dynamics of the merger. They do not penetrate the event horizon. They do not carry information from the interior. They are ripples in the external spacetime produced by the dynamics of the merger, and they allow extraordinary tests of general relativity in the strong field regime. But they provide no window into the interior. The Laser Interferometer Gravitational Wave Observatory has already tested general relativity through black hole merger events with extraordinary precision. The measured gravitational waveforms match the predictions of numerical general relativity simulations to within measurement uncertainty. Einstein's equations, again, are correct in the strong field regime outside the event horizon. What no instrument can tell us is whether the firewall exists. What no observation can confirm is whether information is preserved or lost. What no telescope can reveal is whether the singularity is a physical reality or a signpost toward the next theory. We are building the best instruments that physics allows, and those instruments can only probe up to the boundary. The boundary itself, the most extreme case of time dilation in the universe, the place where the compound hazard of general relativity and quantum mechanics is most acute, remains permanently beyond direct empirical reach. That is a hard truth. It deserves to be stated clearly. Part 8. The human dimension of infinite time. What it means that time stops, and why that should disturb you. I want to spend some time here, before the synthesis, on what this means for the human experience of knowing about this. We are a species that understands the world through time. Narrative is temporal. Cause comes before effect. Childhood before adulthood. Spring before summer. Everything we know, everything we have built, every relationship we have formed, every memory we carry is organized in the temporal structure of before and after. Time is not just a physics quantity for us. It is the architecture of consciousness, and near a black hole, that architecture fails. Not gradually, not as a slow drift that becomes noticeable over extended periods. At the event horizon of Sagittarius A star, the time dilation factor is infinite, not very large, infinite. The ratio of time experienced by an observer at the horizon to time experienced by an observer at infinity is not 1,000,000,000 to 1. It is unbounded. For every finite duration of proper time experienced by someone at the horizon, infinite coordinate time passes for the external universe. The external universe ages without bound. Stars are born and die. Galaxies evolve. The cosmic microwave background redshifts further into invisibility. The current era of star formation, which has been underway for roughly 12 billion years, ends. The universe enters the degenerate era, then the black hole era, then finally the dark era when even the most long-lived stellar remnants have decayed or evaporated. All of this happens, in principle, in the external time that corresponds to a finite proper time at the event horizon. This is not a thought experiment designed to be comfortable. If you were somehow able to hover just above the event horizon of Sagittarius A star for what felt to you like one subjective second, and then were extracted back to the external universe, the external universe would have aged by an effectively uncountable number of years. Everyone you knew would be gone. Earth would be gone. The sun would be gone. The galaxy would be unrecognizable, probably merged with Andromeda, probably named something no one is alive to remember. The universe would be old in a way that makes the current age of 13.8 billion years look like the first paragraph of a very long story. 1 second. And in that second, from your perspective at the event horizon, you experience normal time. A second is a second. Your heart beat roughly once. Your neurons fired normally. Your watch ticked once. There was nothing unusual about the experience of that second from the inside. The horror is not in the experience. The horror is in the comparison. In the gap between your second and the universe's infinity. Close to the event horizon of a black hole, time dilation can reach arbitrarily large values relative to a distant observer. Arbitrarily large, not bounded, not asymptotic to some finite maximum. Arbitrarily large, all the way to infinite at the surface itself. There is a word in physics for a quantity that goes to infinity, a divergence. Divergences in physical theories are almost always signals that the theory is breaking down, that the model is being asked to describe a regime it was not designed to handle. In general relativity, the divergence of time dilation at the event horizon is not, in the classical framework, a signal of breakdown. It is a prediction of the theory. The theory says time dilation is infinite at the event horizon. The theory does not say this is approximate, but as we have discussed, quantum mechanics cannot coexist with this prediction without contradiction. And so the divergence in classical time dilation at the event horizon is also, implicitly, a marker of where the classical framework ends and the unknown begins. Time does not actually stop at the event horizon in some absolute metaphysical sense. Time stops in the sense that the rate of proper time for a hovering observer at the horizon relative to an external observer at infinity goes to zero. A hovering observer at the horizon would need to be accelerating infinitely hard to maintain position. No physical engine produces infinite thrust. No real object can hover at the horizon. The limit of infinite time dilation is approached but never reached by anything with mass or finite energy. The event horizon is thus a boundary with an extraordinary property. You cannot hover on it, you can fall through it. And once you fall through it, the question of what time means, what information means, what causality means, is governed by a physics we have not yet discovered. The compound hazard, defined. 2 systems, 1 location, a new kind of problem. We use the compound hazard framework at Crisis Horizon Labs because some situations are not adequately described by analyzing each component in isolation. A hurricane hitting a coastline with a pre-existing drought is not just a hurricane plus a drought. The interaction creates new failure modes. The dried soil does not absorb water. The risk of flash flooding and slope failure is different from either hazard alone. The emergency response systems designed for each individual hazard are not designed for their interaction. The physics of time dilation near black holes is a compound hazard in exactly this sense. System 1. General relativity. The most rigorously tested theory of gravity in history, confirmed to extraordinary precision from the precession of Mercury's orbit to the gravitational wave signatures of black hole mergers, produces exact predictions for time dilation as a function of position in a gravitational field. Those predictions are not approximately correct. They are correct. System 2. Quantum mechanics and quantum field theory. The most rigorously tested theory of matter and forces in history, confirmed to precision levels that make it the most accurately predictive scientific theory ever developed, produces exact predictions for the behavior of quantum fields, including the behavior of quantum fields in curved spacetime. Those predictions include Hawking radiation and the unitarity of quantum evolution. At any location in the universe except near an event horizon, these 2 systems operate in different regimes and do not conflict. General relativity handles gravity at scales where quantum effects are negligible. Quantum mechanics handles matter and forces at scales where gravity is negligible. The compound hazard does not arise. At the event horizon of a black hole, both systems are simultaneously relevant and non-negligible. The spacetime curvature is extreme enough to produce significant quantum effects, specifically Hawking radiation. The quantum state of the radiation is entangled in ways that general relativity's smooth geometry cannot accommodate without violating unitarity. And the precise location of the conflict is the surface of infinite time dilation, This is the nonlinear risk. This is the new kind of threat that our theoretical models were not designed to handle. Not a threat to physical safety in the immediate sense, a threat to the integrity of our models of reality. A breakdown in the theoretical infrastructure that underpins our deepest understanding of causality, information, and the nature of time. The emergency response system we have for this, the toolkit of theoretical physics, is inadequate to the compound hazard. We have general relativity tools. We have quantum mechanics tools. We do not have quantum gravity tools because we do not have quantum gravity. The tools do not interact correctly at the critical location, and the critical location is defined by the divergence of time dilation. Every approach to resolving the information paradox, whether complementarity, firewalls, islands, holography, or something not yet proposed, is an attempt to design a new tool for a problem that current tools cannot solve. We are in the position of a structural engineer who knows a building is under compound load conditions that the original design codes did not contemplate, and is being asked to certify structural integrity without any applicable standard. The building stands. Sagittarius A* is there. The black hole is real. The event horizon is real. The time dilation is real. The compound hazard is active, and we do not have the framework to fully characterize it. And there is one more dimension to this compound hazard that deserves explicit statement. The word time in the phrase time dilation is not metaphorical. It is the same time that governs the arrow of causality. The reason effect follows cause. The reason information from the past cannot be erased, which is what unitarity and quantum mechanics really means at its deepest level. Causality and unitarity are both expressions of how time works in physics. Gravitational time dilation, at its extreme near an event horizon, interacts with both. When time dilation diverges, causality itself is stressed. When Hawking radiation carries information in a way that violates the smooth causal structure that general relativity predicts, unitarity is stressed. The compound hazard is not just a conflict between two theories, it is a conflict about the nature of time itself. About what time is, what it does, and whether the version of time described by general relativity and the version required by quantum mechanics are the same thing. At every other energy and length scale in physics, the answer is effectively yes, they match well enough. But at the event horizon, the margin closes to zero. The two descriptions of time are incompatible, and we do not have a third description that reconciles them. Part 10. The signals we are watching. What the next decade of physics might reveal. There are experiments and observations currently underway or in development that have a direct bearing on the compound hazard. The Next Generation Event Horizon Telescope will probe the photon ring structure of Sagittarius A* with sufficient resolution to distinguish between general relativity and some proposed modifications. If the photon ring geometry deviates from general relativistic predictions, it would signal new physics in the strong gravity regime. If it matches precisely, it continues to confirm the validity of the Kerr metric in the observable exterior. Neither outcome resolves the interior problem, but both constrain the theory space. The Laser Interferometer Space Antenna, the space-based gravitational wave observatory planned for launch in the early 2030s, will detect gravitational waves from a class of sources called extreme mass ratio in spirals. Stellar mass compact objects spiraling into supermassive black holes over years or decades. These in-spiral waveforms trace the detailed geometry of the Kerr spacetime with extraordinary precision, mapping the time dilation structure at various radii from the event horizon. Any deviation from the Kerr prediction would be immediately apparent. This would be, if it occurs, the first empirical evidence of a breakdown in classical general relativity outside the event horizon. In theoretical physics, the approach called string theory has, over the past 2 decades, produced the anti-de Sitter conformal field theory correspondence, which establishes a precise mathematical duality between a theory of quantum gravity in a particular type of curved space and a quantum field theory without gravity on its boundary. This correspondence has been enormously productive for understanding the information paradox in tractable model cases. The island formula mentioned earlier was derived using this correspondence. The holographic encoding of black hole interior information is described within this framework. But the correspondence applies to a specific geometry, anti-de Sitter space, which has a negative cosmological constant, while our universe has a positive cosmological constant. The extension to realistic cosmology has not been achieved. The approach called loop quantum gravity proposes a quantization of space-time geometry itself, replacing the smooth manifold of general relativity with a discrete network of quantum states at the Planck scale. In loop quantum gravity, singularities are resolved by quantum effects. The infinite density at the center of a black hole is replaced by a region of extreme but finite density. Some models in loop quantum gravity suggest that the interior of a black hole eventually bounces, transitioning to an expanding region that may be connected to a different exterior geometry. These bounce scenarios have implications for the information paradox and for the nature of time at the singularity. But loop quantum gravity has not yet produced a complete theory or a confirmed observational prediction. There is a third observational avenue that gets less discussion than it deserves: gravitational wave echoes. When two black holes merge, the merged remnant rings down like a struck bell, emitting gravitational waves in what are called quasinormal modes. The frequencies and decay rates of these modes are precisely predicted by the Kerr metric. Every merger event detected by the Laser Interferometer Gravitational Wave Observatory has matched these predictions. But some theoretical proposals, motivated by the firewall argument and other attempts to resolve the information paradox, suggest that the event horizon is not the smooth, perfectly absorbing membrane that classical general relativity describes. If the event horizon has some kind of structure, whether a firewall, a quantum membrane, a fuzzball as in some string theoretic proposals, then after the main ringdown signal there should be additional, weaker pulses of gravitational waves reflected from that structure. These are called gravitational wave echoes. No confirmed echo has been detected, but the sensitivity of the Laser Interferometer Gravitational Wave Observatory network is increasing with each observing run, and the planned upgrades to the detector sensitivity, known as Advanced Laser Interferometer Gravitational Wave Observatory Plus, will improve the detection threshold significantly. If echoes exist at the amplitude predicted by some models of horizon structure, they should become detectable within the next observing cycle. If they do not appear, that constrains the class of models that predict them. If they do appear, it would be the first direct observational evidence that the event horizon is not the structureless surface that classical general relativity describes. The echo search is effectively a direct probe of the regime where the time dilation diverges. If the event horizon has structure, that structure exists in the region where time dilation is approaching infinity from the exterior. The gravitational wave echo, if it exists, would be a signal bounced off the surface of infinite time dilation. We would be, in effect, measuring the reflection coefficient of the boundary where time stops. That experiment is ongoing, right now. Every merger event recorded by Laser Interferometer Gravitational Wave Observatory is analyzed for echoes. The results constrain the models. The silence so far is itself information. What all of these approaches share is the recognition that the compound hazard is real. That general relativity and quantum mechanics cannot both be fully correct at the event horizon, and that the resolution, whatever it turns out to be, will require a new theoretical framework that does not yet exist. The question of what time dilation near a black hole truly means, not in the sense of calculation but in the sense of physical reality, is not a question that current physics can fully answer. We can tell you the numbers. We can tell you what the Schwarzschild metric predicts. We can tell you what the Kerr metric predicts. We can verify those predictions to extraordinary precision in the observable exterior. We cannot tell you what is actually happening at the event horizon itself, in the region where those predictions diverge, because that is where the theories conflict. We are watching. We are measuring. We are building better tools. And we are, every generation of physicists who works on this problem, closer to the framework that does not yet exist. But we are not there. And that honest reckoning, that admission that the most successful theoretical program in human history has hit a wall at the surface of infinite time dilation, is the thing that deserves to be said out loud. Conclusion. The people nearest the edge. Let us bring this together. We began with a number: 4 million solar masses, the black hole at the center of our galaxy. We trace the machinery of time dilation from its origins in Einstein's field equations to its verification in every global positioning system satellite, every atomic clock flown on an airplane, every gravitational wave detector. Time dilation is not theoretical. It is infrastructure. It is corrected for in the technology you use today. We explored the Schwarzschild geometry, the idealized non-rotating black hole, and found that the time dilation factor goes to infinity at the event horizon. An infalling observer crosses in finite proper time. An external observer never sees the crossing happen. Two valid descriptions. Two incompatible timelines for the same event. We explored the Kerr geometry, the rotating black hole that matches real astrophysical objects, and found that frame dragging amplifies the strangeness further. The ergosphere forces co-rotation. The Penrose process extracts rotational energy. The time dilation structure is more complex, more extreme, and more directly connected to the jets and accretion dynamics that we observe in the universe's most energetic phenomena. We confronted Hawking radiation and the information paradox. The discovery that applying quantum mechanics to the event horizon produces a conflict with the unitarity principle that has no accepted resolution. We walked through the firewall argument, the Almheiri-Marolf-Polchinski-Sully paradox, and the uncomfortable conclusion that at least one of the foundational principles we use to describe reality must fail at the most extreme case of time dilation in the universe. We acknowledge the coverage gap, the tendency to treat this crisis as an academic puzzle rather than as a fundamental rupture in the foundation of human knowledge about the physical world. The asymmetry between how much this problem deserves and how much public attention it receives. And we noted the instruments we are building, the measurements we are taking, the observations that are, right now, probing the exterior geometry of the time dilation field around Sagittarius A star with unprecedented precision. And the fundamental limit? None of these instruments can look inside. Here is the thought I want to leave you with. Right now, at this moment, as you watch this, there are objects falling into black holes. Not in some distant hypothetical, not in some far future. Right now, stellar material accreting onto Sagittarius A star, light from stars behind the black hole bending around the event horizon, photons getting trapped in the photon sphere, orbiting the black hole in unstable circular paths, their clocks running slow relative to us. And right at the event horizon's surface, in the framework of the external universe, time appears to stop. Whatever is at the event horizon in any given moment is, from our perspective, frozen there forever. Not moving, not experiencing time, hovering at the edge of the region where physics as we understand it is complete. But from inside that event horizon, from the perspective of anything that has crossed, the universe has continued. An infinite duration of external time has passed in a finite internal interval. Everything we know is gone. Every star, every galaxy, every generation of scientists who tried to build the framework that could describe what happened at the crossing. We will never hear from anything that has crossed. We will never receive the report. The compound hazard, the collision of general relativity and quantum mechanics at the surface of infinite time dilation, will continue to operate in silence at the center of our galaxy while we build better telescopes and derive more elegant equations and edge, generation by generation, closer to the theory that does not yet exist. There is something I want to say about that silence specifically, because silence, in physics, is data. The fact that we have not resolved the information paradox in 50 years is not a failure of effort. Some of the most brilliant people who have ever lived have worked on this problem. Hawking worked on it until his death. Penrose, Susskind, Maldacena, Polchinski, Witten, Strominger. The list of physicists who have dedicated years or decades to this problem is long and luminous. The silence is not from lack of trying. It is from the genuine depth of the problem. It is from the fact that the resolution requires new physics, not better use of old physics, not a more careful calculation with existing tools. New physics, a theory that we do not have, that no one alive has, that the universe is withholding until we get the question right. The people nearest the edge of this problem right now are not the people nearest the black hole. Nobody is near the black hole. The people nearest the edge are the theoretical physicists spending their careers on the information paradox, on holography, on quantum gravity, working on a problem whose full resolution they may not live to see, knowing that the answer is there, somewhere in the geometry of a thing 27,000 light-years away, encoded in the behavior of time at a surface that no instrument can directly probe. Those people are doing the hardest work in science. And the honest thing to say is, we do not know yet. The most extreme case of time dilation that actually exists in the universe points directly at the most fundamental gap in human knowledge. And that gap has no clean name yet. If you are watching this, think about that. Not as a curiosity, as a situation. We are a civilization that has learned enough to know exactly where the edge of our knowledge is. We can point at it. We can photograph its silhouette. We can measure the time dilation gradient approaching it with extraordinary precision, and then the equations stop. And the silence after that is where the next century of physics lives. Stay with that thought. Stay with what it means to stand at the edge of what is knowable, looking at something real, something verifiable, something sitting at the center of the galaxy we live in, and to say with complete honesty, we understand the approach, and we do not yet understand the arrival. That is where we are. That is the compound hazard. That is the terrifying truth about time dilation near black holes. If this changed how you think about time, or about what we do and do not know, I want to hear about it. The comments are where this conversation continues, and if you want to go deeper on what breaks down at the quantum gravity boundary, the next video picks up exactly where this one ends. The physics does not get more comfortable, but it gets more precise. We keep watching.